Hello everybody. What you're seeing on the screen right now is a chart from my notes, and it's a table of what we call the VIF-TAD equations. So these equations work for describing motion, but only when you have constant acceleration. And we call it VIF-TAD because the common letters are often V, I, F, so final velocity, initial velocity, time, acceleration, and distance. So a little nickname we have for these equations is VIF-TAD. If you have changing acceleration, so non-constant acceleration, these equations don't work. Okay, and so then you need a different set of equations, or even no set equations at all. You just have the equations, the functions that describe the motion, and you would have the principles of calculus to be able to get from position to velocity to acceleration functions. So with that in mind, we're going to take a look at question 8 from chapter 2. Question 8 asks this. It gives us some functions for velocity. Velocity is a function of time. It asks which of these could be used or could fit into the table, this table 2.1, from the notes and from the textbook. Right. So some things to keep in mind. If the acceleration is constant, that means that the velocity, the function for the velocity, has to be linear. And we see that here in this first equation, right? This is a linear function. You could write that, that looks like y equals mx plus b, right? Where t is the variable, and then a would be the slope, right? So if the acceleration is constant, that means that the slope of the velocity graph, the velocity function, is constant, unchanging. That means it's got to be a straight line. And also that means that the highest order of the position function would be quadratic, squared, right? So we've got that here. This is displacement, but same idea. Position, displacement would just be, the final position, initial position would be in the function. So keeping that in mind, just from that quick realization that the v function has to be at least linear, is a linear? It is, right? It's horizontal, but it's still a line. What's the slope of the line? 0. So this is, v equals v naught plus at. That could be used because v naught is 3, and the acceleration is simply 0. B would not work, right? This one here, because there's a t squared in it. Okay, and so if it has a t squared, think about what this function would look like. It would be a parabola. That would mean you have a changing slope, and that would mean a changing acceleration. Okay, C is linear. V equals 3t minus 4, so 4 is v naught, and the acceleration is 3. Right. And then D, v equals 5t squared minus 3. Again, you've got t squared in there, so this does not work as a VIF-TAD equation. So A and C are our answers. Now, if we add calculus, then that helps as well, because we can take the derivative of this function with respect to time, and that'll give us the acceleration function. And then we'll be able to see, by looking at the acceleration function, is the acceleration constant or not. So for A, right, if the acceleration function would simply be 0, the derivative of 3 is 0, so A equals 0, which is what we said before. There's no acceleration. If we take the derivative of B, then we would end up with 8t plus 2. Obviously, this is a changing acceleration. As time goes on, then the acceleration is changing. Not constant acceleration does not apply to this table. It's not a VIF-TAD function. Here, v equals 3t minus 4. The derivative of this, a, would be 3. Acceleration is 3. Constant acceleration, so this works. D, the acceleration function would be 10t. As t changes, the acceleration would change also. And so this is not a VIF-TAD equation, does not apply to this function. And you need calculus to evaluate this type of motion. So hope this helps. Thanks for watching. Please like and subscribe.